Extension 2 integration. In this first lesson we'll review the standard integral table and see how we can use substitution methods to rearrange integrals to make them standard integrals. You should all be familiar with the table of standard integrals that's provided at the back of the HSC paper. You need to make sure you rip that off so you can refer to it throughout the exam as you need. The whole idea behind looking at standard integrals is that we want to rearrange expressions we're given so that we get a standard integral so we can evaluate it. I'm not going to go through specific examples with those, but I am going to go through some examples involving substitution. A couple of non-standard integrals that you might find useful. The integral of du over root u is 2 root u. The integral of du over u squared is minus 1 on u. Obviously all these are plus a constant. The integral of log x dx is simply x log x minus x. Now we will prove that using integration by parts, but it is a result you can actually just quote and use. Integral of tan x is log of sec x, which is also minus log of cos x. In fact, we can actually have a generalized result here. Integral of a complementary trig ratio is minus the log of the complement of the answer. And that can be useful to use that instead of having to rearrange with a substitution. If you don't remember it, of course, you can use a substitution to solve these problems. For example, if we wanted to integrate cot x dx, we know that cot is the complement of tan, which was up there in our previous result. Therefore, the solution will be minus the log of cosec x, because the complement of sec is cosec. Which of course we can write as log of sine x. So that's just a useful result if you want to save some time and not have to do a substitution. Now we're going to cover a couple of integrations by substitution. For example, these all come from the chain rule, and basically we use substitutions to make integrals standard, and then we can use our table of standard integrals to evaluate the actual integral. Remember, it's very easy to differentiate a function, but it's not so easy to actually see how to integrate all functions. And basically there's a huge table of standard integrals that you'll discover, and the whole process of integration is looking for the way to rearrange particular expressions to make them a standard integral. So for our first example, we're going to try and integrate x outside of 4 minus 5x squared all cubed dx. So we're looking for a substitution, and the substitution we're going to choose here is let u equal 4 minus 5x squared, so the bit that's inside the brackets. The difference between extension 2 and extension 1 integration by substitution is in extension 2 you are not always given the substitution. So basically what we're looking for is a function where we have the derivative as well as the function itself, so we can actually make a straight substitution. Once we've decided we're going to let u equal 4 minus 5x squared, we differentiate it, getting negative 10x, and we rearrange it to say that x dx, the expression we actually have in our original function, is equal to minus 1 on 10 du. Now we can go ahead and make the replacement. I'm replacing the x dx with a minus 1 on 10 du, and I'm replacing the 4 minus 5x squared with a u cubed. Then it becomes a straightforward evaluation because the integral of u cubed is simply u to the 4th on 4. So our expression simplifies to be minus 1 on 40 u to the 4th plus c, and then resubstituting our value for u back into that expression gives us our final solution of minus 1 on 40 outside of 4 minus 5x squared all to the power of 4 plus c. Now of course you can differentiate that and ensure you come up with the original expression. Example 2. Often our integrations with substitutions involve trig functions. In this case we've got the integral of sine x to the 4th, sine x all to the power of 4 cos x dx. So we're looking for a substitution, and the one we're going to substitute for is sine x, so we're letting u equal sine x, and the reason we chose that is we know that du dx is cos x, which is the expression I already have there. So I've already got a cos x dx, which means I can make a straight substitution du for cos x dx. So rewriting our expression, it simplifies really quickly to become the integral of u to the 4th du. which we can evaluate to be 1 on 5u to the 5th plus c, and then resubstituting back in for our value of sine, and we get our final solution as 1 on 5 sine to the 5x plus c. So you can see how something that looked very complicated with the correct substitution was very easy to simplify. If you find after making a substitution it doesn't actually make the original expression any simpler to integrate, then that's probably a sign that you've either made a mistake or you need to try a different substitution. Because let's face it, we could have substituted for cos x. Wouldn't have made it any easier, but we could have done that. Example 3. Slightly different when we have some limits. So here we've got the integral between 0 and pi and 4 of e to the tan x over cos squared x dx. Now at first glance this looks a little bit complicated, and we might have to have a bit of a look around to see what we can actually substitute. Now remembering from our table of standard integrals, we know the integral of e to the u is just e to the u. So exponentials are really easy to simplify. So that probably gives us a bit of a hint that we should be letting u equal tan x. Now let's go with the flow here and see what the derivative of tan x is. Now the derivative of tan x is sec squared x, which of course we can rewrite as 1 on cos squared x. Now that's very convenient because that's what we have in our original expression. So we can do a straight substitution du for 1 on cos squared x dx. Performing that, the only thing we need to do differently when we have limits, well, you don't have to do it now, but I think it's often easier, is we can change our limits, and that just means we don't have to resubstitute back later. When x is 0, u is tan of 0, which is also 0. And when x is pi on 4, u is tan of pi on 4, which is 1. So our original expression simplifies down to the integral between 0 and 1 of e to the u du, which is an awful lot more simpler than the previous expression. And of course we know the integral of e to the u is just e to the u, putting our limits on the outside there, and throwing them in, we get our final value of e minus 1. For our final example, we're going to have a bit of a look at some common log expressions. In this case, we've got the integral of 1 on x log x. Now looking at that, we should remember from our table of standard integrals that the derivative of log x is 1 on x. So if we let u equal log x, then du dx is equal to 1 on x. Now once again, that's a nice result because we can do a straight substitution du for 1 on x dx. Evaluating our original integral with that substitution, it simplifies down to the integral of u du, which is a half u squared plus c, and resubstituting in our value of u, we get a half log x all squared plus c. Hopefully that'll help you with the first exercise in Extension 2, Integration by Substitution, just to help us warm up. And remember, our goal is always to make a substitution that makes the expression closer to a standard integral.